Okay, so hope you have worked out the question yourself. If so, you should be able to verify. You should be getting the acceleration as 2 meters per second square, and you should be getting the normal reaction as 115 newtons. That's pretty easy because you just substitute over here. So F is 25 newtons into cos 37 is equal to mass, which is 10 into E. So A becomes 25 into cos 37, which is 4 by 5 divided by 10. So that's how it becomes 2. And it's SI unit, so it's in meters per second square. And similarly, normal reaction becomes equal to the sum of mg plus F sine 37. So that is 100 plus 25 into 3 by 5. That is how this becomes 115. Okay, so this is the conclusion of this question, people. So hope you were able to work this out. Okay, next example, we will look at a situation on an inclined plane again, because that's a very common type of example and also a very important type of example. So we have this smooth inclined plane kind of situation. So this time the angle of inclination here is 30 degrees, and this is a smooth surface. Now what we've done is we placed a block of mass m like this, and we are applying a force F like this parallel to the inclined plane. So a block of mass m equal to 5 kilograms is placed on a smooth inclined plane as shown. So the first part, if an external force F parallel to the inclined plane as shown in the diagram is applied such that the block remains at rest, find F and normal reaction. Take G as 10 meters per second square. And second part, if F is equal to 35 newtons, then find the block's acceleration, if any, and normal reaction. So just try out this question next, people. So same thing, you have to start with making the free body diagram. Okay, so anybody got the answers in this yet? Okay, so see what all forces will be acting on this block. Let's understand that first. So apart from the external force which I've already shown, there will also be, as you can see, there will be mg acting vertically downwards, right? And there will be normal reaction, which will be acting like this, the direction perpendicular to the inclined plane. Like this. Okay. So when we make the free body diagram, you have to take those forces into account. The forces we have to take into account while making the free body diagram is the normal contact force, which acts like this, the weight of the object, which acts vertically downwards, and the external force which we are applying along the inclined plane. F normal reaction and mg. So this is the direction of the inclined plane. This is the direction perpendicular to the inclined plane. So remember, the inclined plane itself is at an angle of theta equal to, in this case, 30 degrees with respect to the vertical, sorry, with respect to the horizontal. So in this diagram, what happens is that this angle again becomes theta. So in the first part, the block is at rest. That means the acceleration is 0. So what we will do in the next step is we will take so now we know mg is equal to 50 newtons, okay, because the mass was given to us as 5 kg, and we know theta is equal to 30 degrees. This is the information that is given, and what we have to find, we have to find normal reaction and we have to find force. Okay, so we will take x-axis along the inclined plane, that is the direction of f, and y-axis along the perpendicular or the normal, the inclined plane. So we will select our system of xy axis like this. We will take this direction as our x-axis along the inclined plane and perpendicular to the inclined plane as our y-axis. Okay. So we'll do that, and next we will resolve the weight mg into components, x and y components. So when we resolve mg into components, see what's going to happen here is mg is a force which is acting vertically downwards. Okay. Whereas our x and y axis are like this. This is the direction of our x axis, this is our direction of our y axis. So this angle is theta. So when we drop this, and when we drop this perpendicular, so the component of mg along the negative y axis, ये कितना हो जाएगा? ये हो जाएगा mg cos theta, because this angle is theta. Okay. And the component of mg along the negative x axis, ये कितना हो जाएगा? ये mg sin theta हो जाएगा, because this angle is 90 minus theta. So this step is the resolution of mg. Okay. So now use this and find out the value of f and the value of normal reaction given this information here. Find this out. Okay, so anybody is getting the answer? Okay, so let's look at a final free body diagram with the forces resolved. So after resolving mg, the forces are like this: normal reaction force F, and then mg's components, mg sine theta and mg cos theta, and the acceleration is 0. And we are taking our x and y axis like this. This is our x axis, this is our y axis. So net force should be equal to 0 because acceleration of the body is 0. It's at rest. So along the x axis, we have F minus mg sine theta is equal to 0. That means F should have a magnitude equal to mg sine theta. So that means F should have a magnitude of 50 into sine 30. So that means 25 newtons. That is the magnitude of F. And similarly, along the y axis, we have n minus mg cos theta 0. That means n should be equal to mg cos theta. So 50 cos 30 degrees. So 25 root 3 newtons. This should be the magnitude of the normal reaction. Okay, so just note down this result, people, and then we'll come to the second part of the question. Right, so hope this is clear, people. Now work out the second part of the question, please. Yeah, Gajanfar, your answers are correct. Okay. Normal reaction will not be affected by the force because we are applying it parallel to the inclined plane. But because this time the force is 35 newtons, so you will have an acceleration of 2 meters per second square, and the normal reaction will not be affected. That will remain 25 root 3 newtons. Okay. So after resolving the forces and all that, it's pretty much the same type of free body diagram. Only thing is the value of F is different. So there is acceleration up the inclined plane. So what will happen in this case now is that on this body, the external force we are applying is now 35 newtons, whereas the component of weight that is acting against that, that is less. That is F sine theta. Its component is F cos theta. It's 25 root 3 newtons. It's 25 newtons. Okay. And some normal reaction like this. And as usual, we are taking this as our x-axis and this direction as our y-axis. So you can see now F is greater than mg sine theta. Therefore, the block accelerates up the inclined plane. Okay. So it has an acceleration in this direction. So along our x-axis, what is happening is x component of acceleration is a. Along our y-axis, the y component of acceleration is 0. So accordingly, our equations should become like this: F minus mg sine theta is equal to ma. So 35 minus 25 should be equal to 5a. So this gives us our acceleration of 2 meters per second square. And along our y-axis, n minus mg cos theta should be 0. So there's no y component of acceleration. So what is happening is, because we are pushing this block with a force which is greater than mg sine theta, so it is having an upward acceleration like this. Okay, so hope the working is clear to all of you here and the example. Okay, next thing we will move on to now is mechanical systems with another type of force called tension. So next we will look at mechanical systems with a thread or string, okay, or rope or chain or anything like this attached. So we will look at something called tension. We generally denote with the symbol T. So this tension is a type of force. It is a force that acts along the length of a thread or string or chain or whatever when it is tight, okay, or stretched by external forces. So to understand this better, let's just look at the situation. You have let's say on a smooth horizontal surface, you have just placed a rope loosely. So it's kind of bundled up like this. So this is a rope placed on the surface. So this is right now in a loose state. So it has no tension. But the moment we change that situation to a situation where the same rope is now, instead of being in a loose kind of state, it is under tension because it is being pulled, let's say, at both the ends with some force. So if two people are applying force along the chain like this or the rope like this, so now what is happening is, due to forces F on either side, okay, the rope is now in a tight state. So it develops a force of tension T along its length. So that force of tension T now acts like this. At this end, whoever is applying this force will experience an equal and opposite force equal to T. So this tension T will be equal to the external force we are applying because of the action reaction principle. So whatever force is applied at this end of the rope applies an equal and opposite force to the external agent who is applying this force. So that's the reaction for the action F. So that is the tensile force or the tension T. So just make a note of this. Then we'll see more examples. So another term that is used sometimes for this thing, that when the rope or string is in a tight state, it is also said to be in a taut state. So you see the term taut in any textbook or something, you should understand that it means that the string or the rope is under tension or it is tight. Okay, so let's look at some more example situations in which we have a thread or a rope in a taut state. So one very common situation is when we are using a rope or a thread to suspend an object vertically, like a block or something. So because of the weight of the block, what will happen is that this will develop a tension. Or if we have a situation where, example, on a horizontal surface, we have two blocks which are connected by a thread, and then what we are doing is we are pulling this system from one side with some force, some external force. So the system develops some acceleration like this. But as a result of that, this thread is again under tension. So it develops the tension T along its length. Okay, so we'll understand the situation numerically also, but first just get familiar with the concept of a taut string in different circumstances. One important point here is that a massless string. So what we mean by massless is very light or of negligible mass. So a massless string or thread always develops uniform magnitude of tension at every point, including both ends. So we'll understand this more through examples next, but make a note of this first. Okay, so let us understand this with some numerical examples. So let's take the situation. Okay, let's take this situation where we have this block. And this is a light thread, which means that it has negligible mass. So given that the block's mass, let us say 2 kilograms, and acceleration due to gravity is 10 meters per second square, we want to calculate the tension T, the thread. So this becomes a very simple situation. The tension T acting at the two ends acts like this. So when we make the free body diagram for the block, so we can see that the block is at rest. So its acceleration is zero. But there are two forces acting on it. Weight, which is acting vertically downwards, and tension acting vertically upwards. So tension has to balance mg. So the tension in this case has to be 20 newtons. So this is the situation that the tension T balances the weight mg of the block. So that's why it develops a value this much. Okay. So note down this example quickly. This is the most basic example of calculation of tension. From this, we will look at more interesting situations. Okay, so next up, let's look at a slightly more complicated version of this earlier example. So in this next case, what is happening is that we have this time we have a combination of two blocks. Okay, so like this. So blocks A and B are of masses 20 kilograms and 30 kilograms. Take G as 10 meters per second square. Both the threads or the strings, whatever, are light, so their mass is negligible. So we have to find the tensions T1 and T2. So this should be fairly easy example. Work it out. Find the tensions T1 and T2 in each of them. Okay. So all you have to do is make the free body diagrams of the individual blocks and find out. So the hint to you is make free body diagrams. And solve for T1 and T2. So just try this out, people. Okay, so let's work this out quickly. So if you look at the free body diagram of the first block, for the block A, there are actually three forces acting. There is tension T1 acting upwards, there is tension T2 acting downwards, and then there's a block's own weight, like this, okay, and its acceleration is zero because it's at rest. So the equation we will get from this is that T1 balances the sum of T2 plus mg. Okay, so T1 should be equal to T2 plus 200 newtons. So that's our first equation. Now similarly, if you look at the free body diagram of the second block B, yes, you got the answers, Gazenfar? Yes, very good, that's correct. So if you look at the second block B, you can see the forces acting on it are only two. There is T2 and weight of the block, and this is also at rest. So its acceleration is zero. So T2 should balance the weight. Okay. So T2 should become 300 newtons. That's the second. Okay, because that's the way the masses were given. So that's it. Now from solving these equations, you can easily see that if you substitute this in equation 1, you'll get T1 is equal to 500 newtons, and T2 we've already got 300 newtons. Okay, so hope this application is clear. Now next example for you to solve, something which again has an inclined plane. So this angle of inclination is 37 degrees, and this is a smooth inclined plane. On this there is a block of mass m placed like this, and the block is connected by a light thread which is attached to a wall like this. Okay, so the light thread develops a tension like this. So given the mass of the block 5 kgs and g is equal to 10 meters per second square, want to calculate the tension T in the thread. Work this out quickly. Should not take you more than a minute. Yes, that's correct, doesn't it? Very good. So you can consider the forces acting on the block as weight mg and normal reaction n. You can understand in this diagram, this angle will be 37 degrees. So when you make the free body diagram, we'll have to take that into consideration. And now what I'll do is, in the free body diagram, I will show tension along the inclined plane, normal reaction perpendicular to the inclined plane. But I'll show mg in the form of components. So there is the component of mg down the inclined plane, which will be mg sine theta, and there's a component of mg normal to the inclined plane, which will be mg cos theta, and the block is supposed to be at rest. Acceleration is z. So again, we are breaking mg into components like that. What we're doing is we are seeing that the gravitational force of mg with respect to our inclined plane and with respect to the normal to the inclined plane, it's like this. This angle is theta. Okay. So therefore, the components of mg become like this. This component is mg cos theta, and this component is. So this is the step where we are doing resolution of mg with respect to the inclined plane. Okay. So doing that step, we come to this free body diagram. Okay, and we see that what is happening along our x-axis, along our y-axis, the forces are balancing. So that gives us the tension. We'll use the fact that sine 37 is 3 by 5, cos 37 is 4 by 5, and along y-axis, normal reaction is balancing mg cos theta. So the normal reaction here will be 40 newtons. So hope this example is fully clear. Okay, so people hope this question is clear. Let's wind up with one final question for today. So we have these two blocks, and we have a light thread connecting the two blocks. And now we are pulling this combination of blocks from one side with a force, horizontal force F like this. So given the mass of the block A is 4 kgs, mass of the block B is 6 kgs, and the force F is 20 newtons. We have to find the acceleration of the blocks and the tension in the string. So in this question, what you will see is that the moment you apply this force, this string has a tendency to get stretched like this. So it develops a tension like this, and it's a light thread, so there's a uniform magnitude of tension everywhere. Okay. So it's all down to making the free body diagrams of the blocks. So for the block A, the free body diagram will look like this. So weight is balanced by the normal reaction acting on it, but the horizontal tension T acts like this on it and provides with an acceleration A. So the equation for this becomes T is equal to mass into acceleration. So T is equal to 4A. That's our first equation. And of course, normal reaction is balancing weight. So that is not really important for us here. For the second block, yeah. So for the second block B, the free body diagram has weight and normal reaction like this. But in addition, it also has tension acting backwards and the horizontal force we've applied that acting forwards, and it has the same acceleration E. So for this, along the x-axis, we have the equation F minus T is equal to mass of B into acceleration. So F is given to us as 20. So 20 minus T is equal to mass given to us as 6. This becomes our second equation. Whereas along the vertical direction, which balances the weight. So this is not really important. So now next what we have to do is we have to solve equation 1 and 2 to find acceleration and tension. So note this down and try the solving part yourself quickly. Okay, so anybody has solved the two equations and found out the tension? Yes, Gazanfar, that's correct. Very good. So you will get acceleration A as 2 meters per second square, and accordingly you will get the tension as 8 newtons. Okay, so that's pretty easy. Just add the two equations and you will see you'll get rid of T and find out the acceleration, and then substitute the value of acceleration in equation 1, so you'll get tension again. So solving of simultaneous equations for multiple variable, unknowns, etc., is going to be something important in this chapter, apart from free body diagram and vector resolution. All right, so people, with that we conclude this third session of Newton's laws of motion. So we have discussed about the important type of force of tension that acts along a thread through this today. We will continue with this in the next lecture, and we will look into systems which have pulleys. Okay, so you can prepare that from your textbook for the next time. Pulley based systems, so block and pulley type of systems, and of course more systems on inclined planes, etc. Okay. And continue working on the exercises from your HSC textbook or from your module of iit and sub. So that's it for today. Thanks for attending, everyone.